So for this video we're going to do an example problem, and this problem states that the sodium ion of mass 3.8 times 10 to the minus 26 kilograms is missing a single electron. The sodium ion is accelerated through a potential difference of 250 volts and then enters a uniform magnetic field of strength 0.5 teslas. Assuming the magnetic field is perpendicular to the motion of the sodium ion, what is the radius of the sodium ion's path due to the magnetic field? Alright, so ultimately our goal is to use our equation here where the radius is equal to mass times the speed divided by the charge over the magnetic field strength. So the mass is given in the problem, the 3.8 times 10 to the minus 26 kilograms. The charge we know because the ion has lost one electron, so that means it has an electron hole equal to 1.6 times 10 to the minus 19 coulombs. And we're given the magnetic field strength in the problem, 0.5 teslas. So we have to figure out the speed of the particle because it's been accelerated through a potential difference. So we do have to be careful. This is speed, so it's a lowercase v, not capital V for potential difference. Now remember, potential difference is equal to work per unit charge. So the work needed to get something through a particular electric field against the electric force. However, I've just written potential energy here because initially our charge would be at rest. So in essence, we're just taking all of our potential energy that we get from our power supply and turning it into kinetic energy here. So this is why for potential energy here, I subbed in 1/2 mv squared for the kinetic energy. So I can plug in my 250 volts, and that's going to equal 1/2 times the mass, so 3.8 times 10 to the minus 26 kilograms, times the speed squared, divided by the charge, so the 1.6 times 10 to the minus 19 coulombs. So that gives us a speed of 4.59 times 10 to the 4 meters per second, which we can then plug in over here, and get the radius is 2.18 times 10 to the minus 2 meters.